The floor is yours, Amany.
Okay. Can you see my screen now? And does it change between agenda and title?
Perfectly,
Okay.
on this side.
Okay. Welcome and good afternoon or good evening, based on where you are. It's an honor to be with all of you today. And in the next 45 minutes, we will discuss cardboard prototyping and make hands-on activity, building a smart project. So stay tuned and thank you for joining me. My name is Amany Ayman. I have worked in Sana'a Tech and Fab Lab Egypt for almost 4 years now. I worked as an instructor with various ages of students who are still in school or adults and professionals. I liked it so much, so I wanted to build better experiences and activities. So I now work as a learning designer, developing technical content and learning journeys. Our agenda and what we will talk about today is why use cardboard prototyping, low fidelity and medium fidelity prototypes, roadmap to build a low fidelity prototype, and at the end, we will have a hands-on activity called Music Band Project. We are all familiar with messy wires when working with smart projects based on boards like Arduino or microbit and so on. Do any of you have any idea what is the function of any projects we have in the images? I see servo motor, buttons, LEDs, 7 segment, but what is the project? Probably we can't tell. So how do we enable students to materialize smart projects and test their function? To be able to address that challenge, we recommend using cardboard. So in this picture, we see a knob, a hose, and the screen is typing water level. And from the size of it, it seems like it is designed to put a glass in front of it. So it's probably a water dispenser. So the cardboard just now helped us understand what is the project comparing to previous images of just breadboard and messy wires. Also, if there is a movement, we can test it and see it running on real objects, not just running or moving in the air. Now, some of you may ask, are cardboard prototypes is the end product and doubt, will it really achieve the objectives or will it be stable? No worries, I will share with you best practices based on our experience through a summer innovation program we had with girls between grade 8 and grade 11. Approach number one is cardboard prototyping is the final product, yes. When learning objectives are focused more on electronics and programming or smart projects, we like to add cardboard prototyping to electronics and circuits so students can materialize those projects and make them come to life. We call adding both together is low fidelity prototyping. In the summer program I mentioned, girls built a hackathon, a city full of cardboard. We will just have a glimpse. The topic was building a smart city based on cardboard. So by the images and videos, we see all the wiring and electronics are enclosed inside their prototypes. And we can figure out what is the function of each model. So there is smart lights or traffic lights, advanced advertising board, or smart trash bin. So cardboard really helped girls to build up their ideas and making models. Second approach is when learning objectives are focused more on building smart projects using digital fabrication tools. We recommend having low fidelity prototyping before introducing CAD and digital fabrication. You may wonder why and what is the importance of going through low fidelity prototyping first? Well, before making a model, students have many questions to figure out, such as size and total dimensions. Students start asking, will we make the project big or small? Will it have enough space for all our wiring and components? Also, user interface. Students may wonder, how will the user interact with our projects? Where to put LCD screen or buttons or knobs, speakers or sensors, and so on. Last but not least is movement. Students start wondering if we have a motor and that it will control a handle or rotate in some way, how to achieve the required movement. All these new considerations we just talked about when making a smart project design is developing in the phase of low fidelity prototyping, as students have the capacity to learn and make mistakes and waste some material, as it's just cardboard and it's a cheap material, easy to craft and so on. So they can edit their design quickly or even make new prototypes. As it has shorter time periods comparing it with digital fabrication. After that, students gain بقى new acquired skills learning CAD design and digital fabrication, like laser cutters or 3D printers. So at the end, they can make projects more functional with harder materials than cardboard, like wood or plastics, or even make more complicated designs, 3D designs using 3D printer, for example, which we refer to as medium fidelity prototypes. Here is another project which was a final project for the girls in the summer week. I will just speed it up a little. The girls went through all the phases we talked about. So they first made coding and building circuits. Then the best photo we saw cardboard prototype, which they already mounted buttons and put the whole circuit inside of the project. Then they made بقى made the design using Tinkercad and then transformed it to a hardware using laser cutter and 3D printer. And now we can see the final project running and being tested on its function. After we discussed why use cardboard prototyping and learning journey of low fidelity and medium fidelity prototypes, now I will walk you through the roadmap of how to build a low fidelity prototypes. First stop in our roadmap is the design concept. In early stages of any project, students just have an idea about the project or just a name. I want to make a car, I want to make a toaster, and that's it. To materialize that idea, we need a design concept asking following questions. Will it stand or will it be stationary or will it move? And if there is a movement or a function that needs movement, what type of movement will it be? Will it be linear or rotating? Second stop is the enclosure. Students may want the projects to have unique shapes, not just basic boxes, like cylindrical shape or hexagonal or whatever. How do we enable students to make good enclosures with various creative shapes? for their projects. First of all, we let students know what the anatomy of our material we are using, the anatomy of cardboard, how the cardboard is built up, and how could we use the corrugations to support the shapes we are building. Second thing is knowing when to use which tool, when to use cutters and when to use scissors, how to use them safely as they are just little girls, which shapes to cut by scissors. So using scissors is better when cutting circles or corners, but when using just a straight line, it's preferable to use cutters, for example. Another technique is folding, which makes us able to use less glue and also have a neat looking shapes, just like the picture we are seeing. The technique is also called scoring, where we just cut one side of the material and leave the other perfectly fine. Then we fold it using our hands to get various angles. Lastly, bending technique, which is, as the picture shows on the right, it enables us to build cylindrical shapes or cylinders or rounded corners. It is similar to folding, the last technique, but here we cut many lines to be able to transform the straight hard cardboard into a bendy one. Third stop in our roadmap is total dimensions. In this phase, students start thinking what will be the size of the project, and the answer will be based on user experience. Will it be held? So I need to consider hand size, or will it be worn on my head as a helmet or faces my eyes? So I will need to consider standard face size. Second thing to consider is components inside the project or our circuit. Of course, to do so, students must first complete the circuit and wiring, then make the project bigger by an offset. So in this photo, we prepared the circuit wiring, then determined the total dimensions by an offset of 3 or 4 centimeters in length and width. Fourth stop is assembly of electronics. Assembly of components is simply making openings in our enclosure faces for our components. We don't need to show the whole component. Actually, we don't need to see the PCB at all. So we just, the output element, which is the lead matrix itself. So we make our cutout a square with the same size of it and hide the rest of the PCB in the inner side. Same goes for input components as well. Most of input components need to be exposed on the outer faces as the user interacts with them, or so that they can sense physical qualities like air or temperature if they are sensors. So here is a demo of a push button exposing just the button, and the rest of it is hidden on the inner side, and also where we connect wires. And so same goes for motors, as we just need the horn or the shaft appearing from the motor. And so we cut out a rectangle for the case of the servo motor and slide the motor through. So the horn or the part we will attach a hand or whatever on the outside. One of the final stops is fixations. There are many types to glue or fix components on the outer face, but some of the gluing techniques are permanent and can harm the electronics. So we recommend using the ones that are easily to be removed later, like duct tape, for example. And also many components have holes for screws, and using them is easy and quick. Also, using screws in low fidelity prototypes give students ideas of how same components will be assembled in medium fidelity prototypes as well. Finally, enclosing wires. After enclosing the whole project, we can see the outcome. I will demo the video. As we are seeing right now, there are no visible wires and it looks neatly done. This was a project, a smart lamp, where we have a light sensor and a knob. We can control them and control it on the light source. And this is the project after finished. Finally, we have reached the most fun part of our journey. This will be activity applying the roadmap we just talked about. It's a music band project. As you see, those are very cool band members. You can also customize yours. I will be sharing templates for this project on the chat after we finish. This is a smart project where the input is a light sensor, where we can see it down below in the right. Yes, that tiny circle down there. When the light sensor detects dark, it means the party is running. So the output components start working. The servo motor moves the arm on the guitar and start playing music. The LEDs are in the eyes, and the lit matrix showing expressions on the mouse, and the buzzer is playing different tones, and we placed it at the robot's nose. The whole project components are in some way in one face, which is the front. But to be able to enclose all the components and wires, we added sides in a 45-degree angles, turning it from a 2D shape to a 3D in some way. So the whole project has only 4 faces: 1 front, 2 sides, and 1 back. In this slide, I hyperlink the PDFs. So just by clicking on body parts, it will open a PDF. So to replicate this project, we prepared templates, which are the drawings in the image in front of us. The template is a cutting template. So the only thing you will need to do is print it on an A4 paper and glue it on cardboard and start making your project. As we can see, we have all the basic parts, which are the arms, face, components, face cutout components, LED and LED matrix and buzzer and so on, and the guitar as well. Here are other template of the front face where will we be mounting servo and light sensor. And this face is where we will glue the parts we just mentioned. The template, this is the template of the sides. Both sides are right angled triangles, so I put them together, making a square. So this is both sides. And finally, this is the back face template. As for components mounting, the servo motor is controlling the arms as we just described. So we need to just the horn to appear, but that won't be stable as it rotates. So we cut a rectangle and let the servo slide through it, and it will be appear front and back, just like the images. For the light sensor, we don't need the whole PCB to appear, just the sensing element, which is the resistor itself. So we make a small circle opening and fix the PCB with tape on the back side. If any of you wanted to customize the project or tinker it, you can change input components other than LDR sensor, for example. You can use a knob or a potentiometer in this photo, for example, or a simple push button. Also, we have other components mounting techniques. We just expose the elements and leave the PCB and wire on the back side. So the face has two LEDs, one buzzer and one LED matrix. Project fixation is very easy, as we just, after mounting all components, we just start gluing sides and back with the front face. You might be wondering, what is the opening door at the back face? Well, after gluing all sides, it will be very hard to access components on the inside. And we all know how easy it is. Jumpers disconnect from pins and from one another. So a solution for this challenge is making a door at the back face or a side to be able to access our circuit and reconnect wires or edit circuit whenever we want or whenever students want. And ta-da! That is the project after finishing, and that is how you can materialize an idea to become a project which is both functional and cool. Now it's time for questions, and thank you for your patience. Please, if you have any questions, you can share it in the chat.
Thank you, Amany. This was very fun. Very fun project. I'm smiling. So if anyone has questions, please feel free. We have a bit of time, so we have time to chat about and ask any question to Amany about their projects and their work.
Hi, Amany.
Hello.
Hi. Sorry, I don't know if I missed it. How long did the whole project take with the students?
I think, will the templates be ready, or you want them to figure out the size and all?
Yeah, if they cut out their own templates and everything from beginning to end.
I think it will be quick, like 30 minutes or 45 minutes workshop.
Okay. Wow.
But first, it depends on how will they write the code and assemble it. So will the code and wiring be ready as well?
Right. Yeah, that's definitely gonna add time as well. I get it.
Yes.
And then as far as the actual the computer, right? The device, are they all Arduinos, or what did you use for all of them?
I use Arduino in this project, yes.
Only Arduinos. Okay, thank you.
Yes. Actually, we use with younger students an Arduino Shield as well. This simplifies the wiring. So it has ground, VCC, and then signal pins. So we just connect them together. Unlike Arduino itself, we use common ground and need to use breadboard as well.
Got it. Thank you.
You're welcome.
Amany, there's a question on the chat. Could you share with us the link for your presentation?
Yes, sure. I will send it in the chat. I sent the slide link, and inside the slides and presentation, you will find all the PDF templates of the cutouts we mentioned.
Perfect. Everyone that wants to access the project can now access. Thank you, Amany. Anyone has any more questions? Feel free to ask.
I might go to a wrap-up about what we talked about, and then come again to have more questions, if any.
That will be perfect.
Okay. Okay. You can see my screen, right? Wrap-up?
Everything.
Yes. Okay. Wrapping up what we talked about today, comparing results between projects on a breadboard and the ones that have a full prototype using cardboard. The difference is huge, as we can test functions better and materialize students' ideas. And also, it helps students to better understand how the products around us is built up, and what components inside, and what sensors, and what might be the circuits inside, and how it takes dimensions inside the bigger picture, so they can link between what they are making and real products around them. Secondly, now we know how cardboard is very useful, bringing smart projects into life in a quick way, and also with a good final shapes, as we talked earlier about techniques like folding or bending. Now, educators with us, you can use these techniques and low fidelity prototyping phases when you are teaching students about programming and circuits, focusing more on building low fidelity prototypes, using just crafting tools and materials with low budget. And if the school or makerspace at school is available, and you want students to make medium fidelity prototypes using digital fabrication machines, adding cardboard prototyping to your process will make students realize many considerations as user experience or total dimensions and so on, what we talked about. All those considerations, students will get them early in the designing process, which will be saving both time and materials, as in Tinkercad or any CAD software, they will need to redesign and re-edit or edit dimensions, and then go again to digital fabrication machine and fabricate it, and it's also failed for some reason, and so on. So by adding cardboard prototyping as a phase before CAD design will help them save more time and materials. Finally, thank you for being with me today. And I have already shared as a slide link in the chat. So we can take more questions now.
Yes, so anyone feel free to question. There are still people joining in. Personally, I found your process very interesting and very well established. Let's see if I can make my thoughts into a question. Do you always use templates, or you have another level for the children to go beyond and start designing their own templates?
Actually, we don't use templates at all with students.
Nice.
I prepared this template just with you today, but students, we throw them in the... And yes, they start thinking about what will be the total dimensions and where to put each element or which component, and they figure it out all by themselves. So actually, in a session, a project like this may take an hour or 1 hour and a half. Just they can think about the code and make the wiring in maybe half an hour or 45 minutes. And the second 45 minutes, they start building it up with cardboard and so on.
And cardboard is easier to make mistakes than wood or other materials. So that's perfect. So if anyone else has questions, feel free to ask. If not, I think we should wrap this up. And have a little 5-minute break, thanks to Amany. That was so on track. Very fantastic.
Do you have any favorite cardboard tools?
Cardboard tools. I think we use the very basic, like scissors, cutters, cutting mats, and so on. It's the basic crafting. I think students, or maybe girls most, they prefer very much the coloring part. If a project has only 1 hour, 1 hour and a half, they can work extra 1 hour and a half just to color it and add extra stuff. Like, let me show you. Actually, the picture of this music band member, the one on the right, the girls made it, and I liked it so much. They colored the guitar and gave it a headband and so on. So actually, they just like colored paper or coloring pens and start coloring everything.
Thank you.
So the picture on the left, I made it myself.
They're both fun. They're both fun. But yeah, the art aspect, the way that they customize and take it upon themselves to explore new venues. That's the power of education and children, right?
Yes, it's most fun.
So I'm going to stop recording. Feel free to jump into other